I know I did this example in class with my second two classes, but unfortunately I did the other example in my 7 a.m., so I'm making a video for it anyway. So those of you who missed class on Tuesday, you lucked out and you can watch another example of trees if you'd like. This particular tree diagram example doesn't tell us what actual letters to use, so we have to read through here and decide what our different events are. And we can see this question says that in a jury trial, suppose that probability a defendant is convicted given guilt is 95%. The probability a defendant is acquitted given innocence is 97%. And we know that 80% of all defendants are truly guilty. So we have four events that we're kind of thinking about here. One, our defendant being guilty. We also have the complement of that, which is the defendant being innocent. Now, we could use guilty complement if we want, or G complement. I'm just going to go ahead and use letters that mean what we actually want to talk about. The other events are about what happens to this defendant, whether he's guilty or innocent, and that's the outcome of the trial. He can either be convicted or he could be acquitted. So those are our four events that could possibly happen. So when we take all of our defendants to make this tree, we can either split based on their guilt or innocence, or we can split based on their conviction or acquittal. We need to figure out which one makes more sense based on what information we've been given. So we have three probabilities, as we always will in our tree diagrams. We can go ahead and underline all those things that we said were our events. And if we're thinking about a tree diagram, we really understand that we have to have one thing by itself and two conditionals. So we kind of have an idea of what these probabilities should look like before we even get started. Because that's what you're going to need. One thing to split, and then once we have the split, two conditionals to split again on. So, looking through this, the 95% is all about convicted given guilt. Well, we can see our nice keyword of given. So here we're dealing with one of our conditionals. Guilt is the word that comes after given, so we know this person is guilty. The probability of convicting them correctly is 95%. The next probability, that 97, is about a defendant being acquitted given their innocence. So again, we have our given. We're dealing with another conditional. As I said, there should be two in these questions. And here we know the defendant is innocent, but the result of the trial was that they were acquitted. There's a 97% chance of that happening. I said but like that shouldn't happen, but that should be what happens. And then the last thing, 80% are truly guilty. So this is what we are going to do our first initial split on, because that's the thing that takes all our defendants and splits them into two possibilities, right? We cannot split on the other one just because we cannot split on convicted versus acquitted because we don't have that information. So option 1, the defendants are guilty. Option 2, the defendant's innocent. So we have probability of guilt, which is 80%, and we have a probability of being innocent. If 80% of our defendants are guilty, that means 20% are innocent. And then remember, this splits a second time. That's the whole tree of this, these branches that keep going and splitting off. And frankly, these can split into more than two. I'm just keeping it at two for simplicity's sake, and we kind of get the idea. So once we have our guilty or innocent defendants, two things could happen. We can convict, or we could acquit. Convict or acquit. So this, remember, is our givens. Our PGA tour, we avoid trees. We have probabilities, and then we have our givens. And then the last piece of our tree, as we move down and multiply, is going to become our, oops, that is not what I wanted, ands. All right, so PGA, probability, given, and and. Now the givens are always going to match here. We know that we started with all the guilty people here, so we know these people are guilty. So G is what's going to go behind the line for both of these. Same thing on this one. We know these people are innocent, so we can put that behind the line. And the only thing we have to do is say, oh, convict, well, we use C to denote convict, and we used A to denote acquit. C and A. And now I didn't leave enough space to do the equals, I'll just do it below. Convicting a guilty person, we do that 95% of the time. Which means 5% of the time we acquit those guilty people, right? We let them go. Remember, all of these little branches will sum to 100, and that's how you're going to get all 6 of these probabilities to get the last 4. Convict and give innocent we don't have, but we do have that we acquit 97% of the innocent people, which means that we convict incorrectly 3% of those innocent people. And then all of these things are going to turn into ands as we multiply. It does not matter what order you write an and in, so you can write guilty and convicted or convicted and guilty. They're the same. I tend to just keep my order the same as the conditionals because I find that's easier for students to just kind of rewrite this and change the conditional to an and symbol. And then to get these, remember, we're just going to multiply down our rows. This first row is going to be 0.8 times 0.95, whatever the heck that is. So we got 0.76, we have 0.8 times 0.05, which is 0.04, 0.2 times 0.03, 0.006, and 0.2 times 0.97, which is 0.194. So we've got all of our probabilities. And remember, we don't end up using these middle probabilities often after we make the actual tree. So you almost want to cross them out and just don't think about them. Everything you do from here on out should be really with these 4 probabilities. So after this, we have 4 questions. And since there are so many questions here, I know I'm trying to make you guys dizzy. Since there's so many questions here, I really think there's a lot of payoff in making that contingency table again. So remember, we want all the things to intersect. So C and G need to intersect. We know that that's a 76% chance of being both convicted and guilty for our defendants. We need A and G to intersect, so A has to be here, and these two should always be complements. Convicted, whoa. Oh, we're good. I got really crazy here. Yes, convicted and acquitted are opposites. So this is 0.04. And if we add those together, we get the total number or total percent of guilty people, which was 80. And we can double check sort of our work here, like, oh, sweet. Guilty was 80%. And then we need innocent to cross with our convicted and our acquitted, giving us back the 20% of innocent people. And we can also get our opposite marginals pretty quickly from this sweet table, so our other totals. And once we have that, it makes the next 4 questions really easy to solve. So if you want to take a moment, pause, try out answering these 4 questions now that you have this sweet table. Okay, so our first question just says probability of being acquitted. Nothing about guilt or innocence. So this is just A alone. From the table, this is easy. There it is, A by itself. We don't want A and anything, we just want A by itself. All right, next one says the probability that a defendant is convicted. Again, nothing about guilt or innocence. So again, we can go straight to the table and just look at our convicted section. Go, okay, that's convicted by itself. Let's put this down. All right, now things get a little tougher. As I said in class, the most common thing for me to ask for are these two, like one of these, the first 2 we did, and this last one. So I'm going to skip to the last one. Here, we have convicted, we have innocent, so we know this is our C and our I. Nothing here with an and or an or between those 2 words. I mean, there's an or here, but that's about gender. The big key word is our given. So this is the other thing that is guaranteed to be on here after that tree, is I'm going to be asking you for the opposite conditional statement, not the ones we used to build the tree, the opposite direction. So this says we know somebody has been convicted, they're already in jail, we're in this category. What's the probability that they're actually innocent? Right? So that's the intuitive way, our part of our whole, or you can use the formulas. Our conditional formula is the and divided by the probability of the thing we know. So I on C I and C is 0.006, and C by itself is 0.766. So there's a 0.0078 chance that this person is actually innocent, so slightly less than 1%. This third question is definitely something I could ask. It's just not a guaranteed ask like the conditional is. This one, we have guilty, we have convicted, and we have our keyword of or. The main takeaway of this particular question to me is this idea that we can pull the ands right off the table. We can pull the marginals right off the table. The conditionals and the ors require us to use the formula or think intuitively about what the heck is going on. So with this or formula, we said, okay, we want them to either be convicted or guilty, right? Those are the two things we care about. If we use the formula, this is the probability of G plus the probability of C, the two by themselves, subtract off the and. And now remember, this happens because we could take all the guilty people, 80%, all the convicted people, 0.766, but we double counted this 76% that were both because we counted them in the guilty and then we counted them in the convicted. So we got to subtract them off because we double counted them. That's how we get out our final probability here, which should be something larger than either of our single probabilities by themselves. So hopefully after this, we've got 3 examples of that tree diagram of our warm and fuzzy question. We also had it on the worksheet today, and there's some in the homework. So hopefully we feel really, really good about tree diagrams.